But I thought I'd start today with something which is a slightly more boring topic, but to my mind, the far more important one, which tends to get ignored in our industry. So for context, we've gone through a fair amount of cycles within our industry. We go through fads, we realize things, we relearn lessons over and over. And some of those have brought us to a place where we went from a fairly simple ability to deal with state in a fairly simple manner through to a very complex state right now. So some of those things, for a time, we liked this idea of canonical. We kind of thought it would be awesome if we could get everything together into a single format. So we had data warehouses with canonical formats. We had enterprise service buses, etc. And we liked this idea of one-to-one instead of point-to-point. We realized after a little while that actually this created a whole lot of delivery coupling, and we didn't like it anymore. So we went more towards microservices. We went more towards late conformance instead of early conformance. And we accepted the complexity that gave us, but we liked the idea that we could deliver independently. We went from monolithic applications, the quintessential Java app, a whole lot of XML stringing together a bunch of to-dos and copy and pastes, giving us a little bit of scaling, backing onto essentially what was a very large monolithic single database. And this had lots of bad outcomes, but it had this very nice outcome that we didn't have to worry so much about how we dealt with the state from an operational point of view. There was lots of business level complexity, functional complexity in what we were doing, but there was this thing in the background that took away a lot of the complexity about dealing with state for us. With big data emerging, we came up with lots of really crazy architectures, right? Lambda architecture was kind of the popular one, which everyone spoke about, not many people implemented. But we essentially went to a state where we had a huge amount of different backing state stores. Everyone labeled themselves as big data, and we suddenly had the emergence of like 4,500 different databases all tackling different problems. And for any given implementation, practically you land up choosing to use a lot of those. And so instead of having this one place where we had this large problem of dealing with state, we've now got lots of places where we're dealing with state. And as an industry, we don't have much conversation around how do we keep moving our entire stack forward, our entire technical space forward, under the weight of all this state, and all we've done is created more places in which state is being managed. So just a little bit about me. So I head up engineering for a part of Commonwealth Bank called Analytics and Information. And we kind of have the group data warehouse, which is a fairly large Teradata instance, and we've got a couple of Hadoop instances lying around. And the overall context for this is that we load all of the data from our source systems, various latency, through our Hadoop instance into the group data warehouse. And there's broadly two downstream use cases for doing this. The first is that people want to consume data, and this is a very, very broad set of use cases. They want to report to the regulator, they want to understand what's going on inside their business, they generate reports, they do self-service, they do fairly basic statistical analysis on the data. And that's largely about downstream integration work, but it's also about supporting a broad range of access patterns for users, and to a large extent wrangling users and their behaviors. And then off to the left, it's more about integrating within product systems. You go through this organizational maturity when you start dabbling in big data and analytics, where you start off going, cool, we're going to build some models. And that's awesome. You show that you can predict things with models. Then you realize, well, now that we predicted stuff, we're going to have to figure out how we get it into production, because it doesn't help predicting things but not actually having that impact our business. And so you spend a lot of time figuring out how you're going to operationalize features, how you're going to monitor features, how you're going to monitor models, so on and so forth. Then you kind of get into the space of, well, now I need to integrate this into our product systems, and the product systems need a combination of analytics and static business rules, etc. And so you kind of get into operational analytics, experimentation, all integrated into the channel systems. And so you land up with these two broad areas of use case. This is a architecture diagram. It's useful internally, but the only reason for showing it here is that a large number of these use cases that I've just described, different access patterns from users, but also different query semantics going into the channels. When you hit NetBank and you want to understand your transactions going back in history, you want that to be an interactive experience that requires certain access patterns, different state store. For the bulk of our architecture, we use more batch operations, different state store, so on and so forth. So this kind of overall architecture requires us to bring a lot of these different state management systems along for the journey. So as a summary, that's the high-level context of what we do. what we land up with today is well over 4,000 batch jobs, about 6 petabytes of state and growing. This is the state stores that we run today. So HBase, Cassandra, HDFS, Cassandra, HBase and HDFS are the primary ones, and then increasingly Influx, Elasticsearch, and in the background etcd and Zookeeper. They come along the journey mostly because for cluster management or for network management, and increasingly OpenStack Swift as an object store. So that's what seems like a fairly simple set of use cases, right? You've got users accessing data and you're integrating into channel systems, and those are the state stores that come along the journey. It's not one big monolithic Oracle, but it's a whole lot of different ones. And we have Oracle, of course. Can't get rid of the relational databases. We run hundreds of services, so it doesn't help to get all the data in one place and present it via interfaces. You've also got to put up dashboards. You've got to make the data accessible through API, so on and so forth. And so increasingly, there's a rather large number of services available. And we run a huge amount of different processing frameworks, MR1, MR2, increasingly Spark, and some ICA off to the side. That's a story for another day. And obviously, you've got environments. And these are all important. Hopefully, they don't all live for all that much time, but the bottom line is that you landed with a fair amount of complexity, right? So with all of that, all those things are necessary, or we think they're necessary. Whether they are or aren't is kind of, you can only tell with hindsight. The bottom line is that you still have to be able to move forward. You can't stop where you are, comfortable with what you are. You have to be able to upgrade. And it's not purely from a purist point of view. You have to be able to upgrade because of lots of practical reasons. As an app developer, I want a nice stable contract with my infrastructure, but the moment that I want some new feature and the infrastructure can't upgrade, I'm fundamentally hampered by it. And that's operating system, Docker, any particular portion of the provider a contract that I have with my infrastructure provider. There's also the requirements around an ever-changing landscape in terms of regulatory environment, especially within a bank, but an increasing understanding of what's going right and what's going wrong, so we understand operational failure better in the face of time. And there's a continuous threat environment. People do practically go after your environment, and you have to continuously upgrade, otherwise they find new and better ways. So as new threats are identified, as those databases are updated, you have to move things forward. So you've got all this complexity, you have this requirement to move forward. How do you deal with those two things? You have to keep pushing that ball up the hill. But in general, it's not a conversation we have often. So before I start talking about some of the technical stuff, I'm going to quickly mention something about culture. I'm not going to dive deeply into it because it's kind of something you could talk about for many, many days, and we'll leave that to the MBAs. But if you don't address the cultural aspects in what you're trying to do here, it doesn't matter what technical solution you come up with, it fails. You can choose a particular architecture, a set of patterns, you can write as much code as you like, but it becomes unsustainable if you don't have the right organizational constructs in place. Conway's law kind of talks about your architecture reflects your communication lines. You can extend that a little bit further to say your communication lines reflect your org structure, which reflect the way that you're funded. And so if you really want to understand a precursor of what your architecture is going to look like, go and have an understanding of what your strategic planning process looks like before that. Figure out what your funding mechanisms are, and that's going to tell you more or less what your architecture might look like in the future. And if you haven't fundamentally addressed the need to move forward in everything that you're doing, your strategy process, the way you've organized yourselves, the people that you've hired, so on and so forth, you won't continue to upgrade. You'll just come to a place where everything is too difficult to move, and you're sitting there going, we can't get off Java 1.6, or we can't get off a particular version of the kernel, regardless of what architecture you choose. So, coming to architecture. I'm going to present a portion of our architecture. A lot of that won't necessarily make sense, so I'll start by saying architecture is about making choices, right? We don't know exactly what it is, but we know they're important choices, and there's a set of functional requirements that we have that I can't go through in this talk, but there's also a set of architectural principles which we've applied, which hopefully give you a bit more context as to the architecture that we've chosen. So the first thing from an infrastructure point of view is we wanted everything to be immutable. And we've taken this kind of to the nth degree. In our environment going forward, you can't, if you want to change a folder on an operating system, it's a pull request. It's not, no one can consider into a box, SSH into a box. We've taken it as far as humanly possible boxes are completely immutable, containers are immutable, absolutely everything is immutable. And we've done this because it just simplifies absolutely everything. And it allows us to incrementally automate away, tool away pain, as long as we can reason about what the environment is and it's sitting in source control somewhere. Cloud is, it means a lot of things to lots of different people. The economic model is someone else's computer. For us, the more important part about cloud is having API addressable resources, otherwise the immutability becomes a problem to actually implement. So we do have a cloud internally, but it's not someone else's computers, it's our computers. We've chosen state locality. So what I mean by this is you take the workload to the data, not the data to the workload. A lot of people reach for an architecture that allows you to scale independently storage and compute. We specifically stayed away from that for two reasons. The first one is that we want absolutely all workload to be non-local to servers. So I want to be able to run any workload anywhere within my fleet, and I can't do that if I've got appliances and other things in there. And the second one is that it becomes really, really easy for us to reason about our network performance. So if you take the workload to the data, the likelihood of you blowing out any portion of your networking infrastructure is significantly less. And we don't feel that we have the economic model to retain an engineering team to look after the network well enough if we went for different scaling factors. We don't want any particular, we don't like pets in our fleet. So if there's a process that's pinned to a server, we want to get rid of it. Right? You want to be able to move anything anywhere, obviously within the bounds of scheduling normality. We've chosen flexible over optimal. So a lot of our workload, if you come and look at any particular workload, you go, it's not awesome right now. It's not optimal for that particular workload, but on average, it's good enough for all of our workload. And we'd prefer that over being over optimal, because in the face of time, the flexibility is more valuable than being optimal. A lot of people get fooled into thinking that because they're in public cloud or public clouds exist today, that they kind of have infinite resource. And the way that they can deal with problems is just to latch into this infinite resource. But practically, you don't have infinite resources. Practically, whether you're in your own data center or in someone else's data center, you're in a closed system. The long-term effects of entropy you have to stare into, you have to deal with. You can't just keep shuffling things around. Shuffling does help. But a lot of the underlying pathologies that you develop over time, you have to actually tackle. You can't just treat it as an open system, because practically it's not. So in our particular case, we have to deal with state management. We can't just build stateless things and rely on a state management service that someone else has built. We have to stare into the state management problem. For a lot of you, that's not necessarily true. For a lot of you get to leverage other services. But for those of you who do actually have to look after services which manage state, you'll find this useful. The final thing is, even if you are leveraging someone else's state management services, all abstractions leak. It's just a guaranteed thing. APIs are useful. They allow us to upgrade independently to an extent. Abstractions are always going to leak the underlying performance, semantics of the thing on the other side of the API, upgrades on the other side of the API, etc. They're always at some point going to break. And so it doesn't matter what you do, you have to tool away that pain. You can't just assume that something like an API is going to keep you safe in the face of time. So with that, this is the simplest way to represent our chosen architecture. And in the context of this architecture, I'll talk about how we deal with stateful upgrades. So at the bottom layer, we have OpenStack, and we use specifically OpenStack Ironic. It's important to have a hypervisor which isn't a hypervisor. On top of that, we run essentially an Ubuntu operating system, which is just there to host Docker. So the way we build the operating system is essentially a Docker file, which gives you a declarative version of the operating system instance, and then we use Ironic to load that onto the operating system, RPMI, PixieBoot, etc. in the background. We use Calico as the network provider for Docker Lib Network. That's mostly because we feel, again, from a networking operations point of view, Calico is much simpler. It's what we know. It's just layer 3 and BGP. And so it's much easier to fit into our existing network operation structures than any of the overlay networking. For resource scheduling, we rely on Mesos for a fair portion of the workload. And then for the Hadoop-centric stuff, it's Yarn. And then on top of that, Marathon, Kronos, various scheduling frameworks on top of Mesos, and Spark, MapReduce, etc. on top of Yarn, and then the apps deploy into there. Now, off to the left of the diagram, you'll see a whole lot of references to continuous delivery integration. These different people who are not interacting with our infrastructure, but they're interacting via a repository into a continuous set of continuous delivery tooling and across into one of those layers. I'm not going to dive into it too deeply at the moment, except to say that the way we achieve immutability is absolutely everything is a pull request. Firmware is code, infrastructure is code, apps are code, deployment is code, and all of that is driven through the continuous delivery processes at those layers. So that architecture hosts our stateful applications and our stateless applications. So what are the strategies one can generically use to deal with stateful services? So the first one, like I've mentioned, is outsource the problem. Right? If you're in AWS, you've got column family as a service. That's cool. It works. Of course, abstractions are leaky, so whatever choice you make, you're going to have to tool away the pain, and that's okay. A lot of people are they hoard state. One really good strategy, which is not implemented as often as I would like, is just delete it. Right? When it comes time to upgrade, nuke it, rebuild it, continue with life. Be stateless as far as possible. So try and push the complexity of state to the outside of your architecture and not to what people need to deal with day to day. I know that sounds hard. It is actually difficult, but it's a valid strategy. And in our particular case, implement some patterns, improve them incrementally, and tool away the pain. So in all cases, you're going to make choices. You're going to experience a certain amount of pain. You're going to have to tool that away, but you've got to be clear on which strategy. In all cases, focus on excess capacity. If you don't have space to move, it becomes incrementally hard. If you can double provision, if you can have 100% excess capacity, your life's a lot easier than if you've got 20% excess capacity. Again, that just comes down to economic models. So let's talk about some really simple patterns for upgrading. This is not like a enterprise integrations patterns. There aren't 40 or 50 of them. There's one or two really, really simple patterns that we typically use when deploying stateless apps, and they're readily applicable beyond just stateless approaches. So the first one is just a blue-green deployment. This is not news to anyone in the room. I've got an existing stack. Someone's consuming it, so I've got a router of some form as a logical construct in the middle. I stand up a new instance of the stack, I put it there, I make sure it's working, I convince myself that it's working through testing, and then I update the routing configuration, and the user is now using the new version of the stack. This is nice because it gives me the space to do the deployment, to test the deployment, and it also gives me a nice rollback strategy. I can just update the router. It doesn't really deal with the underlying problem of how do I keep those two databases in sync, but in principle it's a nice simple approach. You can extend this to rolling upgrades. It's pretty much the same thing, but just happening incrementally. So it's not 2, it's now n. And so I've got a bunch of old services. I've got a load balancer in the middle. I can deploy the new version. So upgrade, new strongly versioned service running. I can do my tests, convince myself it's working, add it into the load balancing pool, remove the old one, and then do that incrementally. Add new ones, remove old ones, add new ones, remove old ones, until I've got all the new ones there. And all I'm really doing in these really simple patterns is I'm incrementally buying down risk. I can do all the testing I want to do up front. I can do all the unit testing, integration testing, and you should do all of those things. But even having done all of those things, still fail in the deployment process. And that's okay, and we need to accept that. And the way we accept that is to accept that risk in a small incremental fashion and limit the blast radius. So, thought I'd just state the obvious at this point. For us, in-place upgrades, not something anyone should be doing these days. I know it still happens for lots of legacy reasons, but if you're in a place where you need to do in-place upgrades, it should be telling you something about your architecture. It means that you've created single point dependencies that it doesn't matter how good those in-place upgrades are, you're asking for trouble at some point. There are going to be operational failures that you can't deal with in your architecture. So broadly, in-place upgrades for us, not an approach. So let's talk about stateful. So stateful services, there's a huge number of considerations, and it's a huge part of computer science research now and in the future, and it's really, really complex, but at the same time, from an upgrade point of view, we need to think about it in a really simple sense. We need to tease back all of the complexity and just go, what's fundamentally happening here? Now, any distributed state store is going to want to distribute portions of the overall partitions or the overall data space and distribute it across multiple running instances of some kind. Servers, VMs, whatever it is, any of your stateful services are going to create replicas or subdivide the data space into smaller blocks and place them somewhere. And there's lots of different placement strategies. And placement strategies are there to try and help you deal with obvious operational failure cases. So this picture will obviously make you think, well, those are racks and those are servers. But it's just a logical construct. For me inside my data center, I'm concerned about racks and servers. But if you're in a cloud, it's availability zones and VPCs or other things. The blocks simply represent logical constructs that you can reason around the operational semantics of those things. You know broadly how often they fail, and given that knowledge, you can place workload and behavior in a way that you can deal with those operational failures as they happen. So in our particular case, it is racks and servers, and we would typically have a placement strategy in the example of HDFS that says 1 locally here and 2 in a remote rack. That, of course, isn't the whole story, right? You can place replicas, you can place sub-portions of the data. You also need to take CAP into account. And you also need to, in the normal running state, take into account consistency versus latency. I'm not going to go into those things in any level of detail, but those are considerations that each of the implementers of a stateful store are taking into account. There's also different data models. There's key value stores, there's column families, there's relational databases, so on and so forth. You've got to take into account atomicity. And you've also got various access patterns. You optimize for read, you optimize for write, scan, single request, etc. And all of this means that you've got a huge number of different implementations. Right? You're on HDFS or Swift or HBase or Cassandra, so on and so forth. And each of them treat these different concerns in very slightly different ways. And it's important to understand these differences because if I want to upgrade underneath one of those state stores or I want to upgrade the state store itself, I've got to understand those semantics in order to upgrade underneath in a way that doesn't break that particular service. So if I want to do a rolling upgrade of an operating system, I've got Cassandra sitting on top of it, I've got to think about those things. I can't just go and upgrade. So let's talk, what is the naive implementation of this? So any of those state stores are trying to optimize around availability or some other thing. And a naive implementation is just to go, well, let's just upgrade one node at a time. Right? So I've got an upgrade duration which increases linearly with the number of nodes that I've got in any particular cluster. So here's some pseudocode. It's kind of Python-esque. For every node that I've got in my cluster, for each node, if it's valid on some notion of validity, is it in a state that I can actually go and perform an upgrade? So is it busy with some kind of rebalancing process or something which is operationally important or something else? And I need to be able to understand those things. Is it available right now to do an upgrade? If it is, I need to put it into some kind of maintenance mode, and that's generally either trivial or quite complex, and it depends again on what particular state store you're dealing with. I can then run my upgrade, which might mean rebooting, doing an in-place upgrade, something. Do my health tests, and health tests are actually significantly more complex than it seems on the face of it. There's a lot of questions around subjectivity. So do I test from which portion of the network? Do I understand what those network failures mean in terms of the service? Pardon me. And eventually I can update my status and move through this thing. And obviously these are fairly long-running processes, and because they're long-running, they're pretty fundamentally brittle. Health tests are slow, complex, rely on lots of brittle things like timeouts. Upgrades themselves, similar. So here's an example. This is actual Python code that deals with the CDH, Cloudera Manager interface, to try and figure out whether a node is in a healthy state. What you'll notice about this code, apart from the fact that it's really ugly, is I'm kind of putting it up on the screen for two reasons. The first one is health tests are actually quite hard. And the second one is that generally when you're dealing with these kind of services, the services themselves are optimized for consumer side and not optimized for below them in terms of what functionality they surface to you as a user of those services. So if I want to do an in-place upgrade of a Hadoop cluster, or if I want to upgrade the operating systems or the hardware or anything else below a Hadoop cluster, it's really quite hard to reach and find API that make that safe for me. So in this particular case, you'll see I have to go from a service perspective instead of a host perspective, and therefore I've got to go to every single service, ask it for all its hosts, and then go to that host and ask it for all its services in order to figure out whether I've got something healthy or not. So instead of having this turns into a really chatty, nasty set of API calls. It's kind of N by N instead of what you would hope was being N. And each of those calls is a remote API call and is fundamentally brittle and has timeouts and so on and so forth. And so really this process is not geared for me as a person who's trying to upgrade safely below this cluster. It's geared for users of the cluster, not people providing services to the cluster. And that's generally true as you look across. Cassandra's not too bad, HBase is pretty bad, HDFS, Influx, etc. They don't really provide you with much to try and make these kind of processes safe. So let's move beyond the naive implementation, because that one there, if I have 300 nodes and I'm 20 minutes a node for that process, you can see how this quickly becomes an untenable process. So in order to move beyond just the naive implementation, we have to introduce some other concepts. We can't just rely on the placement strategies and the internal constructs of those services, which are there to provide the availability or the consistency or the read semantics that those services are there to provide. We have to introduce other constructs that allow us to reason about those services in the face of upgrades below them. And so these are called upgrade domains, upgrade groups, something to that effect, and it's surprising how few of the state services I mentioned actually implement these things. And so on the left, you've got your placement strategy, and on the right of your screen, you've got this idea of upgrade groups. And what the service has to guarantee is that when it places blocks or replicas or subsets of the data, it's going to place it based on the operational semantics it knows about, but also that it's not going to place more than one replica or portion of that data in the same upgrade group. It's always going to spread them across multiple upgrade groups. And what that means from an upgrader's point of view then is that I can upgrade that entire group safely without causing operational failures on the service that I'm upgrading below. Of course, I introduce operational risk because I've taken my replication factor down, and so that's inherently there, but I haven't damaged the service necessarily. So what that looks like is something that you can parallelize. And this is like fundamentally important. I need to be able to start an upgrade process and complete it tonight, whether I've got 10 nodes or whether I've got 400 nodes or whether I've got thousands of nodes. I need to know that I can start an upgrade process, complete it tonight, because if I can't do that, I'm always upgrading, and when I'm always upgrading, everyone stops me from upgrading. And the longer the time takes between my upgrade and now, the less likely I am to upgrade. And so over time, you fall back into this process of not upgrading. So coming back to the architecture I proposed, the set of integrations off to the left of the architecture now start to make a little bit more sense. We've gone for immutability, and we've said the way we're going to achieve that is everything is code. And at each layer of this architecture, everyone is following that. Code is code, infrastructure is code, version, codification, etc. But they can't move forward in that form unless they talk to each other or unless the continuous delivery layers talk to each other. And so what I'm saying is, and what the architecture lends towards, is that if you want to deal with stateful services, you have to do a certain amount of vertical integration between these layers. Then if you want to safely upgrade underneath a set of stateful services, you have to integrate the delivery mechanisms of those services, the applications, and the infrastructure. The infrastructure in some way needs to know about the operational semantics of the workload in order to safely upgrade underneath the workload. This is true more or less regardless of what provider you're on or if you're a provider yourself. And the only other way to deal with that is a huge amount of excess capacity or a huge amount of extra testing and tooling, which is geared in a different way. You can't assume that someone else's upgrades aren't going to affect you, so you have to test continuously instead of testing at the time of upgrade. So to kind of make this a little bit more concrete, let me talk to you about the workflow that we go after. So we have lots of repositories. A repository is an application or some kind of module, and then we have repos which represent environments, declarative instances of an environment. And this is the Git workflow that we follow for a particular environment. So you've got the declarative form. These are all the servers, services, apps. These are the particular versions and some metadata that they need. You do a branch off master. You do some work. You issue a pull request. not back onto master, but onto a deploy branch. And it's a protected deploy branch, and it has to go through a pull request process, and it has to go through approvals. But in the pull request process, Jenkins also goes off and derives a build plan. So in the background, we have some tooling we call Mission Planner, which is orchestrated by Jenkins, and it'll take a look at your current declarative version of your environment, your future version of your environment, and it'll automatically derive a build plan for you. That gets attached to the pull request, everyone approves it. Once the pull request merges, you do a deployment into the environment, you do smoke testing of the environment, and then you merge back onto master. Jenkins merges back onto master. And so the point there being that whatever's on master is actually what's running in the environment. And if you land up in a state where the deployment fails, the difference between deploy and master is your system is somewhere in between those states. And when the failures happen, you've got some way to go and start debugging. Here's an example of what that declarative form might look like. So it's for a cluster. For the control tiers for our clusters, OpenStack, Mesos, etc., we also do blue-green deployments. So we would typically deploy a new OpenStack control tier, and then we forklift some of the nodes from one control tier to the other so that we can move OpenStack forward without affecting anyone else. And it takes similar operational semantics into account as I've described. We'll open source that code under Big Tent in the next month or two. So this gives you an idea of what that declarative form looks like. And then the pull request process kind of looks like this. It's not the best picture of Ramon. So you do a pull request, you're showing a change between one declarative form of that file and another. And the CR tool will go off and derive a build plan that says, based on what you've asked me to do, I think I need to add, remove, delete, do the following things. And some of those are going to involve me starting and stopping services, waiting for health checks, so on and so forth. You'll see here that the view of that build plan is still pretty raw. It's kind of a two-string, but the build plan is fully described, well typed, etc. So recommendations: if you're about to go undertake this kind of initiative, or if you're currently undertaking this kind of initiative, if you're having to run stateful services, instrument as much of the deployment as you can. It's true of any kind of system that if you don't instrument enough, you can't do performance management. But for getting anything other than a naive N upgrade process in an automated fashion is just a huge amount of instrumentation and optimization you have to do over time. Those 20-minute reboot times or those 4-minute health checks, because of all of the timeouts, which all seem logical, all become a real problem at scale. Optimize incrementally. So once you've got that data instrumented, don't just optimize everything. Go after the most concrete problem you have. Allow for manual intervention. So this is all about automating upgrades and making that deterministic and doing it often. But quite often strange things happen, right? Overheating fans, poor performing fans, disk failures representing in different ways, etc. At some point you have to be able to step in and manually intervene and make sure that your automation doesn't preclude the manual intervention. Otherwise you find yourself in difficult places of needing to do a lot more than what you expected in big chunks. Encourage people to intervene. I know we don't want people to, we want to tool away any manual intervention, but when failures happen, don't have an environment where people are scared to step in. Encourage people to step in, burn their fingers, tool it away. Prevent pets. As soon as you're building either stateful or stateless services, or you're hosting them in some way, people will create pets. Your users will create pets. They'll start up something and they'll go, it's working, and they'll walk away from it. And over time, it becomes special in its own particular way. And you need to figure out protocols and mechanisms with your tenants such that those things don't become pets. The simple thing is just to kill their workload, but obviously you need to have that conversation up front. And ultimately, all of these things, you can't automate any of this stuff away unless you've got a very clear view on how you're going to test any of it, because all of it is fundamentally brittle if you go about asserting that something is in a healthy state and moving on to the next step in the process without it actually being in a healthy state. So regardless of how much time you thought you were going to invest on building automation testing and health checks, triple it. And that's it for me. Thanks very much, guys.